Okay, hello, good afternoon, everyone. It's 4 o'clock, so we start the webinar. And welcome to this latest edition of the Australian Computing Academy's Digital Technologies webinars. Round of introduction, your presenters today is myself. So my name is Karsten Schulz. I'm the Deputy Academic Director of the Australian Computing Academy. And on my virtual right or left is...
Hi, I'm Dan from the Australian Computing Academy. I'm currently working as an associate lecturer at the University of Sydney. We're working on a new Masters of Education specialisation, which is specifically for upskilling people in digital technologies and particularly around leadership in that area as well. So it's nice to meet everyone.
Thank you, Dan. So today we're going to look into another of our key concepts. You know, there are 10 in the Australian curriculum, digital technologies. Last week, Penny and I spoke about digital systems, and today we're going to focus on specification, and as part of that, also computational thinking. In case you're wondering why computational thinking is not listed as a key concept here, the reason for that is that it underpins everything in the digital technologies curriculum. Okay, so what are we going to cover this week? We are going to focus on specification. We're going to talk about problem definition. We're looking at constraints, decomposition. We also take a peek into the industrial practice. What's happening outside of the school? How does the industry do it or not? And we're certainly covering curriculum links. And as part of the coding and computational thinking part, more computational thinking than coding really, are the pedagogical implications. And we're also going to take a look at international developments. What are other countries doing, and is there perhaps, or are there perhaps things that we can learn from it? Okay, so this one is a classic. I highly recommend it to everyone. If you Google this, what the customer wanted, you find that. And I assume many of you have already seen it. But if you haven't, it's really the thing that explains it all. So if you remember nothing else from this presentation, then perhaps you remember this comic strip here. Obviously, it's about making a swing, and the customer explained it in a certain way. And you can see, well, that's a very odd-looking swing here on the top left-hand corner. But then communication is always such a wonderful thing, because what one person says is not necessarily what the other person understands. So this is how the project leader understood it. The engineer designed it in yet another interesting way. The programmer wrote it like this. The sales executive, of course, described it like this, cushioned armchair. Isn't that wonderful? The project was documented like this, and that's very common. It wasn't documented at all. Operations installed this, which is very little. The customer was built according to this specification. The help desk supported it rudimentary at best, but what the customer really needed was just a tire on a rope. Okay, and this is very common, and it's a wonderful example for specification, because what I explain, someone understands quite differently, and then along the many chains that we have for the construction of something, all sorts of interesting things happen. So if you haven't seen this yet, get it from Google, what the customer wanted. It's wonderful. Okay, over to Dan.
Yeah. So when we talk about specification, that means that we're defining a problem precisely and making it into a manageable problem, breaking it down into pieces and so on. As Karsten mentioned at the start of the webinar, it's one of the 10 key concepts in the digital technologies curriculum. And there's a really good resource, if you haven't seen it already, from the ACA called the Unpacking the Curriculum, where basically each of the key concepts is unpacked and linked back to the relevant content descriptors in the curriculum. So if you haven't had a chance to look at that, that's worth looking to as well. And so in this webinar, we'll refer a couple of times to this sort of overarching problem of, say you gave your students a project where you asked them to design a Space Invaders game, how would they break that project down into manageable pieces? What are the different parts that are necessary to create that game, and so on? So we'll refer to that a few times. And so the whole reason that we specify problems like this is having clarity around what sort of problem we're solving and how we can solve it. And so it's important not to just, I mean, particularly if you're working with students and you get them to do some sort of project, they may want to get in and they may want to start, coding away in Scratch or Python or so on, but it's good to sort of encourage them to step back and plan out, what exactly they're trying to solve, and what problem are they trying to solve, and how can they build a solution that will actually solve that problem. So so like it says there, you can sort of go in and start implementing something, but you do that at your own peril. It's better to step back and think about how to solve that problem. So, Karsten.
And as Dan and I were preparing this presentation, I told him, look, I think I was about 25 years old until I started to appreciate the purpose of specification. So when we do specification, or when we did specification, you would have probably heard about the Waterfall Model. And that's a very big classic, where you start with the requirements, a requirement analysis, and after they are done, then you move into the design phase. When that's done, you move into implementation, and from there you verify, and you move the whole project into maintenance. What we found very early with this model is that it didn't work particularly well, and there were a large number of projects that failed for that very purpose, because they were like late in the verification phase, it was found that the requirements were faulty, and there were key assumptions that were incorrect. And then it was way too late. Thousands of pages of specification had already been written with wrong core assumptions. That's the waterfall model. We don't use it very much these days. If you want to explain the waterfall model in other terms, I think this comic here nails it, and I'm not sure how your resolution is. I'll read it to you. We're planning an expedition to a part of the jungle where no man have ever been. Oh, wow, that sounds exciting. How will you find your way when you are there? Well, very easy. That will be easy. We already spent 6 months to draw the maps. Okay, that's exactly how how the waterfall model worked. Okay, we make all the fine specifications without having any particular knowledge of the terrain we're going into. When people realized that this didn't work so well, they made modifications, said, well, let's not just go one way, let's also be able to go back one step from every stage of the process. So for example, you can go back from design to requirements, or from implementation to design. But that was also a very static model, which worked better than the waterfall model. Over time, that model was taken and refined again, and into what we use now today in the development process, what we call Agile Methodology, or an iterative development process. That means we essentially do a number of steps. We plan, we build, we test, we review. That's one sprint. And from there, we plan and build and test and review a bit more. And then we plan and build and test and review a bit more, okay? Which means that we learn about things as we go through the project, and we improve our understanding of the terrain. And I recently watched probably too much of Apollo documentary on Netflix or Amazon Prime, I can't remember. But it made me realize that the individual missions of the Apollo program were exactly that. That was an agile development process, because they first tested things on the ground. And they had the predecessor programs like Gemini, for example. But even the individual Apollo missions, they took the spaceship into Earth orbit and tested it there. And then they flew to the moon, Apollo 8, but didn't land. And then there was another Apollo mission where they tested the landing. They disconnected the lander from the command module, but they didn't descend all the way. Okay, they came back then. So that mission could have landed. They had everything they needed, but it was not their purpose to land. And only when they reached Apollo 11, NASA said, well, we've tested enough and we're confident enough. We've done enough of these various sprints with various foci. So now we're confident that we can land. And they landed the spaceship. very successfully, and they brought the man back from the moon. So if you want a good example of agile development methodology, I think you can look into the Apollo program. And given the current topic of SpaceX, their successful launch over the weekend, that is something that students might be able to connect to. Right.
So I guess when we think about what's possible in maybe upper primary and sort of 7 to 8 level, there's these different levels, different models of software development. So using that annotation tools, put a stamp in which in the box that corresponds to the different models that you've used. So have any of you used these sort of models? Yeah. So a lot of people using Agile and Iterative or something else, so maybe design process as well. Awesome, everyone uses a bit of different things.
Great, looks like there's quite a majority for Agile and something else, right? So just recapping, like Waterfall versus Agile, okay? So the important thing is that a good specification is always grounded in reality, and the Agile methodology or the interactive approach or the iterative approach allows us to get to know the reality a bit more, okay, through these various cycles. Every time we learn about the reality, we test things. Does it work? Does it not work? Are our assumptions correct or not? And in the past, it's true that we sometimes specified for months on end, only then to find that our key assumptions were incorrect. Okay, but today we do the rapid cycles of specification, algorithm development, and testing. And we're not doing this because we like it so much, but we do like it because there's the solution path that we want to explore, whether it is feasible and whether it meets our customer expectations. Fail fast is the motto behind that.
So going back to unpacking specification, and as I mentioned before, there's the Unpacking the Curriculum resource from ACA, which is well worth a look if you're not familiar with that already. But the way that this is unpacked is there's these 4 sort of main aspects or sort of topics within specification. So there's problem definition, which is really defining a problem that needs to be solved quite clearly, thinking about who the stakeholders are and so on. The constraints, and so we'll give some more examples of that later, but thinking about what the constraints for your particular solution to that problem are, thinking about the requirements in terms of both functional requirements and non-functional requirements, and decomposition, which is all about taking that problem and breaking it into more sort of manageable pieces. And so once we've decomposed the problem and we know how to break it up, then we can start on the the algorithmic work and before we leap into the implementation where we're actually going and coding it. So if you're not familiar with pseudocode, that's sort of a representation of code that isn't is sort of a not specific to a particular language. So what it's often used as a step between, say, flowcharts and actually implementing that code in a language like Scratch or Python or so on. So once we get to that point, that's sort of where we would normally sort of stop the specification. Yep. So one of those aspects that I mentioned is the problem definition. So actually setting out and defining what that problem is, and thinking about, say for example, with that Space Invaders game, that's sort of a large problem. How do we sort of break that down and make it more manageable? And also thinking about who the stakeholders are in that particular problem. So if we're designing a digital solution, who are the people that are going to be using that, and what are the considerations we have to make for them? And the constraints, so as I mentioned before, thinking about what the restricting factors are and how those affect our planned solution. So we talk a bit more about functional and functional requirements soon, but examples of constraints are, say we're developing some solution, what are the costs, and when, can we afford those costs? What are the environmental considerations as well, and that sort of thing. So yeah, next slide.
So an example of constraints here, if you're working on a school-based solution of something like a role system and you're storing student names, then that is a constraint that you need to be aware of. For example, privacy might come in here, which might limit your solution in a particular way. Yep.
And when we talk about functional and non-functional requirements, by functional, we're talking about, the specific purposes and behaviors of that solution. And as we have there, the calculation and the technical details of that system. Whereas when we're talking about non-functional, it's more about, the criteria that we're using to evaluate that system. And so a good example of that, like Karsten just mentioned, is thinking about, for our system, the security of data that's being stored or so on. Also thinking about how can we make our solutions accessible, and what considerations we have to make for those as well.
Security is, by the way, an interesting one here. The border between functional and non-functional is fluid. Like in the past, security was often an afterthought, and security is increasingly becoming an absolutely core requirement of any system that is being used by the public, or in certain environments where security rules, whether it's defense, for example, but also in a school environment. If you're storing student data, you better make sure that the system is sufficiently secure. So it can also be a functional requirement. Yep.
And then decomposition is quite a significant aspect of specification, because we might have a big problem to solve, and we have to figure out how we can break that up and make it a bit more manageable. So Karsten will give an example of that with reference to, creating a Space Invaders game. How can we, take that project and break it into parts to make it easier to implement? And it's all about, taking something that's like fairly complex as a whole and putting it into simpler parts. And when we talk about abstraction and computational thinking, they're very related to that as well.
Okay, so here's the part for us to get active again. Think about the Space Invader games, and that's a great party discussion, like, have you lately decomposed the Space Invaders attack fleet? I mean, I highly recommend doing it on a daily basis. So when you look at this image here on the right, that is screenshot taken from our Space Invaders challenge. And the question is here, if you think about this bottom up, what is the first step, the most simple thing that you can solve? So what I would like you to do to paint the numbers 1 to 5 in the fields here on the left, where 1 is, oops, I'm getting there, where 1 is the smallest possible thing here, the lowest level of granularity. Where would you start if you were to decompose as the Space Invaders attack fleet? So put the numbers 1 to 5 in the column here on the left. Have a go. So there seems to be a fairly broad consensus that we would start with the design of a spaceship. Then the majority seems to think that in the second step, we would position the spaceship. Yep. And then number 3 would be to make a row of spaceships. And then number 4 is not entirely clear at the moment, but it looks like number 5 is making a grid of the spaceship. So number 4, we could say we animate the spaceship. Okay, that seems to be the consensus now, that number 4 is okay. Right? Yeah. Okay. So I'll show you how one way of doing it. I'm not saying that's the only one. I'm just switching to the next slide, but I'll leave your annotations on the screen if that works. Okay. So what we thought is, yes, we also start with the design of a spaceship and then be able to position it, because you need to be able to position it in order to make a row of spaceships, because the spaceships have different positions. But you also need to be able, you also need a position of a spaceship if you want to animate it, because then the spaceships, whether it's one or many, moves. So positioning a spaceship is a prerequisite, whether you want to make a row or animating it. And then we felt that we would animate the spaceship then, because you've got one spaceship. And animating that is easy, because it's just one spaceship that can potentially go into the wrong direction. So it's easy to catch that mistake. Always think from the specification also, how big would the bug be that I need to fix? But it's not the only way of doing it. So then we felt we make a row of spaceships, and those spaceships, they would already be animated. They could animate, they could move around. And the last step is, of course, where everybody agreed, we make a grid of the spaceships that move left and, right, left, right, and left. But you could do it differently. You could also say, after designing the spaceship and positioning it, you then make a row of spaceships and then animate it. So there are often different ways to skin the cat, so to say, and they all lead to the same result. What I would like to show you, and I'm just clearing the annotation here, is how we getting the multitasking, how we did it in the academy when we designed our Space Invaders games. So we followed a storyboarding approach, which I quickly want to run you through. So that's the original storyboard from Space Invaders when we designed it. Okay, so what did we do? As Dan said, it's a communication tool. So we use it as a communication tool within the ACA team and also with our GROC colleagues, because there was some platform work that needed to be done. And we also wanted to have a consensus on how we go about this challenge. Code complexity was a big requirement. It shouldn't be too complicated for the students. And we thought about, okay, how would we introduce that? Do we have a narrative? And we came up with a narrative that the United Nations have developed this global defense system, right? And then there are aliens coming. We later refined that story and added our environmental aspect to it. And those of you who have done Space Invaders would remember that the Zargans have run out of water because of some sort of environmental catastrophe. We then started at the end, said, well, how would it look in the end? Well, we said, well, Space Invaders, we all know Space Invaders. We have all played it, so that's how it might look like, although we've got different spaceships, mainly for copyright reasons. And then we started, okay, one spaceship. Like we started with one spaceship. And then we prototyped the code here. Normally, you wouldn't do that in the specification, but we had to, because code complexity, as I said, was a strong requirement. Don't make it too complicated. And then we positioned it. How would the code look like? Is it still manageable for a student of year 7, year 8? Then we went with 2 spaceships, so an intermediate step between one spaceship, positioning it, and then a row of spaceships. Okay, 2 spaceships. Okay, we can do that. We introduced then functions. Then we had the row of spaceships, a grid of spaceships. So very similar to what you thought when you gave your vote. And then we looked at, okay, now if we animate the thing, and then, okay, and it needs to move back. And you see how the code complexity grew. And at some point we said it's too complicated, and then we had to refine it, which is not in this document here. We also thought in the interim, can we shoot down spaceships, or can students shoot them down with clicking them? That was a concept that never made it into the implementation, for example. That's okay. That's the purpose of specification. You toss up ideas and some come into the final product and the others don't. And we thought, do we need counters? Do we need spaceships moving to Earth? And so on. And then we thought, should we add comic strips into it to make it more interesting for the students, like Calvin and Hobbes, the space adventurer Spiff, Spaceman Spiff. We thought about adding video elements. And if you know the final result, the video elements, the short video clips, they made it into Space Invaders, but the comic strips didn't, largely for copyright reasons. Here's another one, really like it, unfortunately didn't make it. And then we thought, do we need other materials to explain things like positioning a spaceship in the Cartesian plane? Okay, we did that. We thought about rewards and things, and we went with a design from the Royal Australian Navy, adjusted the colors a little bit. But that's why we start with Commander, which is not here. Kids become Captain, move up to Commodore, Rear Admiral, Vice Admiral, and then Admiral of the fleet. So try to make it as realistic as possible. and certain things. So that was our storyboarding approach. It was a great communication tool in the team. Everybody got buy-in. We started with the development, and we kind of knew where we were heading because we had done that preparatory work. It's all good fun making it. So we're opening a bracket now. The bracket is on computational thinking. Okay. So these, what I'm presenting now are the findings of a report that was commissioned by the New South Wales Department of Education in 2019, a paper that James Curran, Amanda Hogan, and myself wrote. And you can find this paper if you just find coding and computational thinking, the evidence, and our names in Google. But I should say the views are just those of the authors. Okay, we don't make any particular claims. So when you look at the current definition of computational thinking, it's a problem-solving method that involves various techniques and strategies that can be implemented by digital systems. Now, Janet Wing, and most of the definitions that you find out there are based on Janet Wing's definition, is formulating problems and the solutions so that the solutions are represented in a form that can be carried out by an information processing agent. So far, so good. What we felt was missing from that definition, they're not wrong, we don't mean to criticize anyone, but we felt what was missing here was that in computational thinking, we have a process where we do a repeated cycling over a problem, okay? So we have an incremental solution and we feed it back into the solution process, and that produces a slow shift over time. And that is then the solution to the individual problem. So we're chipping away a little bit. It's very iterative. Like when a computer does multiplication, it does so by repeated addition. Computers can't do multiplication. And that is that repeated cycling over the problem. And we find that if you look at computational thinking from that perspective, it really is a key difference between the computational thinking approach and all the other thinking approaches that are presently taught at school when you compare, for example, with mathematical thinking, which is more formula-based, or the thinking in physics, which is about forces, and chemistry is about the reactions of the electrons in the outer hull. But in computational thinking, we don't have comprehensive all-in-one solutions, really. It's just, here's a little step, and we apply it repeatedly, and we get to a solution. And that, for example, sits at the foundation of the example of Space Invaders. No? We start with a spaceship. Okay, great. And then we start repeatedly applying rules to it until we get our Space Invaders game. So here's an example, a short video about sorting a list, just to explain that point, not just from Space Invaders perspective, but generally, here's a sorting algorithm. Okay, so what do we do? When you think about sorting a list, what is the smallest thing? It is really just comparing two elements, isn't it? Right? And if they're not in the right order, yeah, then you swap them. Basically, that's it. And you do this repeatedly, and we keep comparing, and we keep comparing, and you see how the solution bubbles up. Okay. So we know at the end of each cycle, we have made one additional position, right? Do this again and again and again until, well, we have to define a stop condition, and the stop condition is there's nothing left to sort, okay? And I think that really expresses for me computational thinking. It's done, wonderful, we've sorted it. Okay, repeated application of a very simple rule. And the hard part about computational thinking is to find that most simple bit, because that requires a lot of abstraction. Okay, right. There was a study done for your information, in case you haven't seen it, by the National Foundation of Educational Research in the UK in 2017, and they had a randomized controlled trial as part of the evaluation of code clubs. And they had two groups, one of them attending code club for a year and the other didn't. Here, 5 students that was. And then they measured it against their performance in the Bebras Computational Thinking Challenge. So in that particular study, they could not demonstrate a significant statistical difference between the two groups, whether they attended code club or not. So the question here is, though, is Bebras the right measure to measure computational thinking skills? Or was it something they did in code club? They asked the questions at the end of the paper, but they couldn't give an answer based on the data they had. Okay, so measuring computational thinking is really hard. So let's look at some of the development overseas. In Estonia, for example, they started in 2012 a program called Prograde Tiger, you might have heard of, which is a mix of ICT general capabilities, design and tech, using the terminology, the Australian terminology, and digital tech. And they put this all together. There's a big focus on technology in the classroom in Estonia. And we couldn't find a publicly available evaluation of the program. It's very much common to most of the programs. The evaluation is really hard to get your hands on. In Finland, the approach is different. There they focus less on programming and more on computational thinking. And Finland surprisingly ranks relative higher in international education tests like PISA compared to other similar Nordic countries such as Sweden, Denmark, and Norway. Okay, because those countries, they score lower, more in line with America, where the focus is on coding. I found that quite interesting. Okay, and the UK, of course, you're all familiar with the approach in the UK. So where most of the approaches in the US, Australia, New Zealand got the inspiration from. There the focus is more on coding and less on ICT general capabilities and digital tech. And they've been criticized for taking that hardcore approach, and they're trying to steer against that. Students have been dropping out apparently as a result of that program becoming too computing focused. So for us, it will be interesting to continue track those development and then compare them between the UK, Finland, Estonia, and of course Australia, how students from these countries then might perform in a future study on computational thinking, which I'm not aware has been designed yet, but if it ever comes, I'm very keen on it. Okay, let's talk about the implications for teaching and teacher professional development by Dan.
So part of our work at the Australian Computing Academy is running professional development workshops and more recently doing these webinars. I've also been involved with the Masters of Education at the University of Sydney, the Digital Technology specialisation. And it's all about, trying to figure out how to support teachers who are learning to teach digital technologies. And as Karsten mentioned, there's different sort of names and focuses of these sort of curricula in other countries. But of course, over here we have the digital technologies curriculum. And one of the challenges with, when we're creating these programs is finding good research and good models for pedagogy in computer science. And partly this is because we haven't really been teaching computer science and digital technologies for as long as we have been other subjects, so other, particularly the STEM disciplines. Things like mathematics have been taught for centuries, but basically, computer science was probably not too widely taught until the 80s, and then it's sort of been phased out and it's more recently sort of come back into the mainstream K-12. So really this is an important area to research and to understand better. Sorry, next slide, Karsten. And part of what we can do is we can provide students with opportunities to follow their interests and create digital solutions related to those. But we have to be careful that the focus isn't just on the coding side of things, but also computational thinking as well. And one of the things that's great about the digital technologies curriculum is it's not just about the algorithms and the implementation, the algorithmic thinking and the programming, but digital technologies as a whole and sort of all the different concepts that are related to that, things like data representation and so on. So another key point there that we have is the idea of not just teaching students these skills because it's about building an army of programmers. It's about giving students the skills and knowledge they need to create with digital technologies. Next slide. And you know, that's something that we have to think about when we're thinking about the pedagogical side, is how do we address the needs of, you know, different students that may not even be interested in digital technologies as a career, but that still deserve the opportunity to learn those skills. So you're probably familiar with the TPAC model of teacher's knowledge. If you're not, I'll briefly explain it, but you may have seen this in professional learning or in your teacher education. And the reason that we talk about this is because, you know, when we're supporting teachers that are learning to teach digital technologies, we have to think about all these different domains of knowledge. So for example, they sort of have those, like the overarching domains of technological knowledge. So that might be, you know, your understanding of how to use computers and sort of more of the general ICT, the pedagogical knowledge. So your understanding about different pedagogical strategies and how to teach sort of more generally, and content knowledge. So your knowledge of basically the subject matter of the subject that you're trying to teach. Yeah, so there's a good comment there in the chat. Yeah, it's not, you know, it's part of teaching digital technologies is helping them understand those technologies that are part of their daily lives. That's a good point. So with the TPAC model, you know, we're looking at the intersections of these different domains of knowledge, and in particular, in this we'll just emphasize pedagogical content knowledge. But that's the understanding of how to teach content in specific subjects. So when we're talking about digital technologies, pedagogical content knowledge, we're talking about strategies to teach content from that learning area. So that's important to note. And as we mentioned in the next slide, one of the challenges is that for us, you know, running professional learning and also doing some work at the tertiary level is, particularly for teachers that are new to this, like digital technologies and particularly programming, it can be quite a challenge because we're trying to, you know, support teachers with the content knowledge side of things, the actual digital technologies content, but also trying to support them in learning how to teach it as well. So that's something that you might have experienced when you're learning yourself or when you're supporting your colleagues that are learning digital technologies. So there is a lot of research being done in this area, which is sort of informing our work at the academy and at the university as well. And there's lots of work to be done. And, you know, as digital technologies becomes more mainstream, not just here, but in other countries where there's new curricula involving these concepts, there'll be a lot more opportunities. So I've just mentioned a model of teaching there that's been developed recently in England, which is quite it's called PRIM. It's a model of teaching, but that's a good example. So the main point is there that while the teaching of computational thinking is relatively new, there's lots of interesting work happening in there, and that's informing our work here at the Academy and at the University of Sydney. So I'll let you go, Karsten. Yep.
Okay, thank you, Dan. And here we close the brackets on computational thinking. And if you're sometimes not so sure about the pedagogy, then you probably can feel relieved a little bit because the pedagogy is not settled yet. It's still under development and we still need to document it. Okay, so let's take a look back into specification at the curriculum. And this is a screenshot taken at our website, aca.edu.au. We've got the slide earlier in the slide deck. And this is where the 4 curriculum authors are coming together and they document and give additional information and so on, all in line with what you find at ACARA, of course. But here they've got a bit more space in addition to the 2-page scope and sequence document that you all have. So we're going to look at that section here. Now I want to unpack specification from the perspective of the curriculum. So after 2 and 3 to 4, you notice the first thing immediately is that there's an overlap with algorithm. So there's no clear separation between specification and algorithm. And if you remember from earlier in the slides, they're kind of fluent. They go into each other, and sometimes we need to jump from specification into algorithm as kind of codified here from F to 2 and 5 to 6. So what are the key terms in specification? What do we need to look out for? Well, there is for the F to 2s, it's following steps to solve a problem. And that from 3 to 4, that gets to the definition of problems at growing complexity. So it's rather simple in 3 to 4, it gets more complicated from 9 to 10. So following and defining are the key terms here. And then we've got requirements, and they kind of get introduced with the 5 to 6 band, data and functional requirements. And we heard about functional requirements earlier. And then 7, 8, we get more requirements: functional, economic, environmental, social, technical, and usability. And then 9 and 10 adds the non-functional requirements. We've also heard about them. And interviewing stakeholders. That means that we take a third-party position here, not just our own view, how great we think that solution is going to be, but also the position of the third party, for example, the customer, someone who's going to use that thing later. And then, of course, 7, 8, and 9, 10 add the decomposition, okay, breaking a problem apart into smaller, more manageable pieces. Okay, so how do we represent a specification? You've seen one earlier, storyboard. That can be a great representation of a specification. It can be plain English, simple diagrams. It can be structured English, like flowcharts, for example. And with these, we need to convey the idea, because remember, specification is first and foremost a communication tool. And we need to find the language that the other party understands. So if, for example, I want to have a specification that my stakeholder, my end user can use, if I become too technical, then it's kind of useless for them. So I need to speak in the language of the person who's going to read that. Okay, but we like to focus on the problem here. We like to focus on the constraints that we have. And we want to point towards a solution with specification without necessarily solving it right away, because that comes later, but we want to break it down into the manageable tasks. So what's the decomposition process? Let's have a look in industry. How do we do it there? And I'm not suggesting do it exactly like that, but maybe it sheds some light on how we can do it. So in industry, we start with a user requirement. Say, what does the customer want? And we also call it the market requirement. Then we go into the engineering requirements and say, what needs to be done in order to come up with a solution? And then we break it down in various steps, in a coarse specification and then a fine specification. We are nudging closer and closer to the algorithm. But we start with the perspective of the customer, because there's no point developing something just because we think it's great if there's no one out there who needs it. Okay, so user market requirement, we ask ourselves, what's the actual problem? Okay, what does the customer want as a solution? Okay, what is the available budget? Who's going to pay for it, right? Is it cheap? Is it expensive? When should it be available? Very important question when you take on a task. What's the timeline? And in terms of industry, you also ask about the market size. Is there a market for 1 or 2, 10,000, 1 million? It would be good to know before we make the investment. The engineering requirements, we ask ourselves questions like, what technology is required to make a solution? Do we have the necessary technical skills? Do I speak that language that is needed here? Do I know the database, for example? Do I know the user interface framework? Important things to know. We ask ourselves, what is this thing supposed to do at its core? And what are the non-functional requirements that we need to consider as well in terms of accessibility, for example? In the coarse and fine specification, we break it further down. We say, what are the key functions or the key modules or the key classes that we need? How will the parts of the solution interact if there are multiple parts? And we express this through text, flowchart, and pseudocode, whatever works in order to convey the idea. And then we're slowly entering the algorithms. Okay. So that was a quick run through. the decomposition process, starting with market requirements, with engineering requirements, and then going into the specification. The important thing is not to overdo it. So it shouldn't be an exercise just for the sake of doing it. It should have a purpose that you want to get more clarity about what is needed, when it needs to be done, and how we go about doing it. Okay, Dan, back to you.
So this is a good example here, and this will be in the slides that we send out to you after today. So if you haven't seen it already, Akara have a bunch of different work samples, and the one that we've focused on here is a Year 7 and 8 app development project. So that would be worth looking at because it does a really good job of showing how specification can be used and provide some templates and that sort of thing if you're looking to do a similar project. So in this particular work sample, it's an app and they provide samples at what are the different levels again? So above satisfactory and below. So that would be worth looking into because it shows a good example of how a student has specified a problem and broken it down into manageable pieces. Was there anything else to add to that, Karsten?
I think what I like here is there's some really good templates in there. Although these are all screenshots, I'm not so sure how you can download those templates. But I think as inspiration and idea, if you're looking for materials in order to support specification in the classroom, you might want to take a look at that. We're not saying they are the best ones. I think they're good. Maybe you've got better sources, and if you do, please share them with us and we will include them in the slide set before we send it out. Okay. We've come to the end. 5 minutes to go. Made it. We hope the webinar added maybe a bit of clarity around the topic of specification and computational thinking. Maybe it gave you an angle to these topics that perhaps you haven't considered yet. Perhaps you already knew that the Apollo program was very much an agile development process, the way how they did it. If nothing else, maybe you can have a great party conversation now in order to decompose the Space Invaders attack fleet, should that topic ever come up. We are going to stop the recording here. So we're going to hang around for a few more minutes. If you like to ask questions, whether via the audio channel or on the chat. In any case, Dan and I would like to thank you for your attendance. Thank you for your participation. And we hope that things continue to go well for you and your students in the classroom. Thank you.